it's a report on something that is not public yet, so we'll see how that goes. It's joint work with Melcher and Jing Wang. What I'll do, I'll explain what we tried to do, and I'll start with recalling basic facts about large deviations, mostly to see later why we cannot do it as easily. So I'll go over first well-known results on large deviations for random walks on say, real line first. So we take IIDs, and then we take the log moment generating function, assume that the distribution has finite lambda, and then we know that you have this statement here, right? That's what we have in mind. So lambda star is, of course, the Legendre transform of lambda. So this is what we want to do on something that is not flat anymore in some sense, and also has what we call degenerate geometry. So we will not have much geometry in this talk, but I will give you one basic example of the setting and explain what the main challenges are. So this is what we want to replicate in some sense in that setting. So, of course, one of the main tools in Rn or Rd is Cramer's theorem. And so I stated here before I again review the basic principles on metric spaces. And so that's coming. And mostly to indicate that we're using some structure that we have from Carnot groups to be able to use something like this. So Cramer's theorem says that the same kind of setting that we have, and then we can reduce this consideration to finding these two bounds, upper and lower bound. And if we have that, we can prove the large deviation principle. So the question is, what are we using from the underlying space, in this case, Euclidean space, to actually use this? And it turns out that if you have a nice metric space, and not too nice, just nothing very special, you can still go through the same thing. So I'm just recalling I know that I'm going through the slides too quickly, but I'll slow down once we get to the real part, which is relatively new for us. That is, I'll talk about Carnot groups and then the setting and the main difficulties there, okay? So the large deviation principle in metric spaces usually starts with saying that, well, we can define what it means to have large deviation principle on, say, Hausdorff topological space first. So we say that we have this rate function, and we assume that it's low semi-continuous on the set, which is assumed to be closed for each A. If, in addition, this set here happens to be compact for each A, then we call I to be a good rate function. So this really doesn't use metric space structure, but if you add metric space to the assumptions here, then we can verify this low semi-continuity on sequences. And this is what we see in many of the formulations of the large deviation principle, what you need to prove something like Cramer's theorem. Okay. So the moral of this slide is really that for us, a good rate function on a metric space. So I will mention this later, that Carnot groups are nice metric spaces, is such a rate function that its infimum is achieved over closed sets. Okay, so this is really a review of some basic definitions or facts from this theory. And mostly I just wanted to review it so that you understand why we're proving what we're proving. Okay, so in some sense, that's not good pedagogically, right? I talked about large deviation principle before I actually define what it means, but I just wanted to justify this definition because we're really talking about metric space. And so we'll say that the sequence of probability measures satisfies large deviation principle with rate function I from this metric space to the half extended line from 0 to infinity. It can take on infinite values if the function converges weakly, and what we mean here on all Borel sets here. And as we said, it's equivalent to, so that was what we kind of referring to proving these two bounds here for all open sets and for all closed sets. Okay, so this is the definition that we should keep in mind. So what we want to do now is take this M, so I have M rho, which is metric space, and replace it by Carnot group, which I'll explain what it is on the next couple of slides. Are we still okay? Okay, thanks. Okay, so of course there are several tools that you use usually in this business, and one of them is the contraction principle. And again, it can be used on metric spaces or even on topological spaces as it's stated here. And again, I just wanted to indicate it. I will not show you, it's a relatively short talk, so I cannot do it, but I will kind of allude to difficulties of using this contraction principle, even though we do use it at the end, but you will not see how, but hopefully soon it will be posted, and then you'll see how it can be done. So more or less it says that if you know a good rate function for one Hausdorff topological space and you have a continuous map to another one, then you can reproduce good rate function there. Okay, so so that's the usual thing that people try to do in this business. So of course the usual reference space would be Euclidean space where you know how to do this. And so the question is, can you do it for something curved like this Carnot group? So it is something that has a non-trivial geometry. So I'll try to explain why it's not that easy, but that's the background of this. So you would think that you can do this, and then we'll see if we can actually do this. Okay. So these are really a review of kind of standard tools on this business, and now we'll slow down a little bit and talk about Carnot groups. Okay, what is a Carnot group? So we'll have a very specific Carnot group, of course, Heisenberg group, what else? And yeah, I thought of giving another example, but it seems that's the example that is easier to still explain. And I think it's good enough for us to see all the little problems or not so little problems that appear. So Carnot group is a group, it's a Lie group, and it's Lie algebra, and we'll have very concrete realizations of that. So its Lie algebra here is what's called stratified. And what this means is that it can be written as a sum of subspaces which are indexed by numbers from 1 through R here. R will be called the step. So this is the step of this Lie algebra, stratified Lie algebra. And what it does, it says, okay, if I take the first one, V1, and bracket with V2, so these are Lie brackets, the usual Lie brackets, you get to the third layer here. So sometimes these VIs are called layers of this Lie algebra. So you start with V1, which we'll call horizontal, and then you move to the next one until you reach 0 here. So the point is that you will reach 0, that's nilpotent Lie algebra, And so the number of steps needed to get to the zero space, to the trivial space, is called step of this Lie algebra. So these Carnot groups are the groups that have this Lie algebra, and they have lots of nice features. So for example, they have dilations, and it's also easy to see why you have this. So if you take, say, V1, V1 here, and you get to V2, then any scaling you do on the first space, V1 should be with the square on the second one, right? Because if you get your alpha to this first layer here, then it comes out a square on the second layer. And this is what this property here says. So this is what we call dilations on the Lie algebra. This is a linear space, so it's really easy to see what it means here. And what this thing here says is that you have the automorphism on at the Lie group level. So just to throw some things here, that these are nilpotent Lie algebras. The corresponding group is a connected, simply connected Lie group, nilpotent Lie group, and because of that, you have exponential and log functions from the Lie algebra to the Lie group, the global diffeomorphism. So we're in a very nice situation in terms of the Lie group's Lie algebras. And I understand that that seems a little bit out of place in this conference, but we'll have a very concrete setting later on. So essentially what we know is that even though the group itself is not linear space, we have this nice dilations that come from the Lie algebra, from the stratification of the Lie algebra. So this is really closely related to how stochastic processes behave on these objects, and I'll mention this later, a little bit later. Okay. So again, we don't have time to go through this, but we can actually identify these objects, very abstract objects, with Rn for some capital N here, where both Lie group and Lie algebra is modeled on the same space. And that's what's called homogeneous Carnot group. So you can actually think about putting a structure different from the usual Rn structure. And of course, the Heisenberg group here is the prime example of this. So you identify it with R3, and then instead of the usual addition here, you have a correction term here, which comes from the standard symplectic form. Okay, so that's the Lie group on this. And the algebra is also a simple object in this case, but we'll not talk about it. Okay, so that's the example we'll have in mind. So what is the geometry of this Carnot groups? As I said, it's a degenerate geometry. So what we have is we have this first layer, which generates the whole Lie algebra, and this first layer is called the horizontal subspace of the Lie algebra. So we can actually write the Lie algebra as horizontal and vertical spaces. So more or less, again, if we are talking about this kind of setting, we have a smaller space that Lie bracket generates the whole thing. And the problem for us will be that actually we only can measure things, how the angles and the lengths on this space of the dimension strictly less than the space where the process will live or the random walk will live. Okay. Are we still kind of okay? Okay. So what is the geometry? The geometry here is what's called sub-Riemannian geometry, but also it's a nice metric space. And first what you do, you introduce the length. And the length is defined here. What you do, you take any path on the group and you take its pull back to the Lie algebra. And if it happens to be in the first layer, so it shouldn't go to the vertical space at all, then we say it's a horizontal path and we measure its length. as I said, we can only do it there, and that's what it is. So it's kind of constrained movement. So you can go up, right? You can go into vertical direction, but you have to do it using the lip brackets from the horizontal space. So you cannot go up directly, but like this. So it's a nice space, as I said, because we have Fermat's condition, that is lip bracket generating condition, which allows us to claim and prove that any 2 points in this group are connected by a horizontal path. And therefore, we can have this distance here. It's not the only distance we have there, but it's one of the nicest distances, which is called Carnot-Chapter distance, which minimizes the length of horizontal paths connecting 2 points. Again, in Heisenberg group, you could write that very explicitly. So I decided not to do it for the lack of time, but I decided to write explicitly what the Brownian motion is in the Heisenberg group. So it's written here. As you can see, it's driven by two-dimensional Brownian motion. B1, B2 are two real-valued independent standard Brownian motions. And the third component here is this Lévy stochastic area process. So you take B1, B2, and it pushes the process to live in the three-dimensional space. So the one thing that I wanted to emphasize here is written below, which says that, that actually one of the nice things about the dilations that we had was that you still have this distance we're using here, the Carnot-Chapter distance, is the scaling that you expect from Brownian motion in Euclidean space is still here, the space-time scaling. That's what this says. Okay, so probably by now you wonder, we're almost over time, right? Where is the random walk? So now it's coming. So, so this is the theorem that I will formulate. I'll talk about it a little bit later, but so this is not the most general result we got, but I just wanted to emphasize certain features of this result so that you can see at least what the difficulties in some sense. Okay. So we start with a Carnot group so step 2 means that it might not be Heisenberg, but something like Heisenberg group. And then we take in the horizontal space, so we take random variables. So this is really just like R2, for example, for the Heisenberg. And we assume the same thing as before here as in the Euclidean case. And then we take what we call the horizontal sub-Riemannian random walk, which is simply you take exponentials of this X case, multiply them, take the measure of that, right? And this is the dilation on the group. So you start with X case here, which are on the horizontal space in the Lie algebra. You take the exponential, get it to the group, take the product, you get something random working on your group, and then you use the dilation. So that's really the random walk here. And then you can prove that it actually satisfies large deviation principle, and you can write the following rate function. So the point here is really that you can prove that you have to really, so you can consider only this horizontal paths. So you don't have to consider all paths, but just horizontal. And this is where the large deviation principle is controlled by this rate function. Okay, so can you say anything more than that? Actually, yes, if you feed in the samples, which are not just sub-Gaussian, but actually, say, standard Gaussian. So again, remember that what we have here, we only doing this on the horizontal space, so we don't see the whole space in the beginning. And then we say we can prove that the rate function actually is given by the energy the energy that it takes to get from the identity of the group to element G in time 1, or 1/2 of that energy. So this seems like not surprising, knowing the Euclidean results, except that we should keep in mind this is not a linear object anymore, so we cannot really use anything like the Cameron-Martin type results or anything like this. So it really has to be proven in our proof. We really do it from, we're not using any big guns until the last moment. So it's really analyzing the random walk on these Carnot groups. Okay, so actually we proved even more that in this case, this equivalently, you can say that this rate function is given as 1/2 Carnot criteria distance to that point from the identity, the square of that. Okay, so of course the first idea that one might have is that, well, it's random walk, so what's the difference between that and just random walk on, say, RD? And the difference is huge because, of course, if you take the exponentials, multiply them, you don't get the exponential of the sum. So essentially the whole business is how you compare the sum of here and what you get from this product. And I'll illustrate it on the next slide in the case of the Heisenberg group. So the last comment that I don't have on this slide that I don't have time for is how we actually saw that these two things are the same. It's a non-trivial fact, has to do with lots of things on, analysis on Carnot groups, but I will not talk about this one. So let's look at the same Heisenberg group case and see what happens. So, suppose in that case, what we're feeding in are random variables xi or xk, yk here. Okay, so these are horizontal here, so it's 0 here, indicates that the vertical is 0. So you take the exponentials of them and multiply them. So in this case, you can do it explicitly using the multiplication rule. And of course, here is a typo because I thought somehow first that doing it with 3 things would be easier, but then realized no. Okay, so what you do then is you see the usual R2 random walk here. That's what it says here. Okay, and the correction term comes here, and what it does, it just takes samples from, say, xi, yi, xj, yj, and takes the symplectic form here, and that's the correction you get in the third component. So if, for example, you fit in here the standard normals, right? So you have normal, 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 and then you fit them in. Each term here will be chi-squared type distribution. So actually what you need to do is you need to look at this random vector now and prove large deviation principle for this one. If you fit in sub-Gaussian, you still have estimates on this form, but that indicates what the problem is in actually proving large deviation principle. So in principle, what you want to do, you want to use some kind of contraction principle from RD, right, or R2D, or whatever you have, no, R2 in this case, or to this 3-dimensional space. But of course, the problem is that, as we know, the stochastic period is not nice functional, even for Brownian motion. So you don't expect this continuity to just drop out of immediately. So you have to do something else before you can use the contraction principle, because it does require continuity of the map you're using. So you cannot just take the horizontal space on the Lie algebra and map it to the whole group. So that's what, so I, of course, did not cover any details here. And I just want to mention, so this is just says that more or less what you need to do here is you have 2 points that you want to compare here, right, with this correction term here. And you can only use horizontally to them. And you need to make sure that these 2 horizontal paths are actually close to each other once you get to these 2 points. So I'll finish off with mentioning a couple of references which are relevant, mostly to indicate why this is different. So one of the things that we tried to do was to identify the rate function, and so this was there are lots of results, but one of the previous papers was by Baldi Carmelina, and I don't think that paper identified this rate function as explicitly as we can do it. We also were motivated in some sense by these papers here. So especially this paper by, so it's random walks on Lie groups. And there are lots of things. So in that case, you really don't have this degeneracy. So you have, so essentially what you can do, you can just use log and exponential map on the Lie group to use the contraction principle, something that we cannot do because we have to keep track of being horizontal every time. And also, as you could see, we use samples which are definitely non-bounded. And for the convergence issues, he used bounded samples, which excluded, for example, normal samples, which means that you cannot really identify the rate function at all. So what I didn't really mention is higher step groups, which we can do. I probably will stop here and we'll take questions if there are any. Thank you.